Now, this video provides a general overview of exponential growth and decay, which leads into application questions for exponentials. Now, you need to remember whenever you see rate of change, that's a derivative, that's the gradient. Okay, now what we're doing is the same as what we've done previously, way back in Unit 2. It's just that we're introducing Euler's number, that E. Now, populations tend to grow at a constant rate. What does that mean? Well, it means that, or it implies that, the change in population is proportional to the population. And you'll see how I've written that there. dp dt, the change in population over the change in time, okay, is proportional to the population p. Now, if we know this, and you look back to when we did do rates of change way back in year 10, constant rates of change, we could rewrite that as dp dt equals kp. So all I've done is replace that proportional sign with equals kp. Now that k is the constant of proportionality. So it means that dp dt is equal to some constant multiplied by the population. Now, in methods, you don't need to know how to integrate that. So how to go from dp dt equals kp to p. You just need to know that dp dt equals kp leads to, if we were to integrate both sides, p equals my initial population times e to the kt. So that's what I have there. So you just need to know that relationship. Now that's for growth. What about decay? Well, the only difference with decay is it's a negative rate. Okay, it's decreasing over time. So my constant is negative. The formula is similar, but again, with that negative in the power. Okay, now we've already looked at mathematical modeling by exponential functions back in Unit 2. All we're doing now, as I've already said, is we're incorporating that exponential e, and we're also going to introduce derivatives by looking at the rate of growth and decay, which we haven't done before. Now, let's compare. In Unit 2, you should remember what I called the golden formula. Instead of remembering all those individual formulas for half-life and all those kind of things, I said you only needed to remember this, and I showed you that every problem could be solved with it. So A equals my initial A times B to the T. Right? Now, all we're doing now is, instead of having B, we have e to the k. So B equals e to the k. We can do that because e is a number, it's an irrational number. They're both constants. E to the k is a constant. All right, so we're just introducing that. And you can see that in the formula. So instead of e to the k, instead of b, we have e to the k. Now, what do the things mean here? T is time. A of t is the amount at time t. A base 0 is the initial amount, so that's when t is 0. And k, as I've already mentioned, is a constant of proportionality. Right? So just remember that B is equal to KT. We could solve all the problems that I'm going to do in the subsequent videos using the method that we did in Unit 2 or using the method we're now going to do in Unit 3. All right, it's just that we're using that E. Now, you need to remember that the domain should be considered because time will always be greater than or equal to 0. And for exponential growth, remember that k is greater than 0, and for exponential decay, k is less than 0. So that's the basis of exponential growth and decay. What I want you to do now is have a look at the videos for the examples. You may want to try and solve the example first. I'm going to do a video per example. But yeah, try as you move through the examples to have a go before just watching the example.